My name is Paul Argyle. My advisor is Professor Philip Sprengel. I'll be discussing our research in the nonlinear analysis and simulations of the Cherenkov-Maser amplifier. This research topic is of interest primarily because of the potential applications that stem from it. Compact, high power, and wideband amplifiers operating in the gigahertz frequency regime have a number of important applications, such as radio frequency communications with ground and airborne systems. Amplifiers in this frequency range are key to achieving the necessary waveform diversity and agility for these applications. In this work, the fundamental limits of the Cherenkov-Maser amplifier in generating high power levels over a wide frequency range is analyzed. The configuration of the Cherenkov-Maser amplifier is depicted in these diagrams. A relativistic high current electron beam enters a waveguide where it couples with the longitudinal modes of the waveguide and transfers electron beam kinetic energy to electromagnetic energy of the output signal. The waveguide consists of inner and outer conductors for combining the fields, a vacuum gap for the electron beam to propagate in, and a dielectric layer for bringing the phase velocity in the waveguide close to the electron beam velocity for energy transfer to take place. This interaction occurs between the subluminal TM mode and a beam mode. Amplification of input signals occurs over a very wide frequency range. Operating frequencies are in the gigahertz regime. Output power levels greater than a gigawatt with an input power of 1 kilowatt and efficiencies greater than 50% have been simulated. Conversion efficiencies can be enhanced by pre-modulating the electron beam density or tapering the phase velocity along the length of the waveguide. Interaction lengths less than a few meters have been simulated, making this amplifier tenable for practical applications. We began our analysis by solving Maxwell's equations in the linear regime to obtain a dispersion relation. A dispersion relation describes the relationship between the frequency and wave number of the system. The dispersion relation for the Cherenkov-Maser amplifier can be written as an electron beam mode coupled with a waveguide mode equal to a term proportional to the electron beam current. By solving the dispersion relation, we can obtain the allowed modes of the system. The modes that cover the largest frequency range are the subluminal TM mode. Subluminal means that the phase velocity is less than the speed of light, and as depicted on this diagram is blue, is close to the electron beam velocity depicted in red. In the absence of the dielectric layer, the waveguide TM modes would have no axial electric field component. However, we found that with the dielectric layer, the TM mode has an axioelectric field equal to its transverse electric field component divided by the relativistic mass ratio. Thus, since this subluminal TM mode covers the largest frequency range and has a significant axioelectric field component, this is the mode that we want to excite in our amplifier. We also obtained estimates for the phase shift and growth rate in the linear regime, but we are really most interested in the nonlinear physics. The nonlinear formulation of the Cherenkov-Maser amplifier was done under the assumption that the system was in the steady state operating at a single frequency. Under this assumption, every electron in a beam segment has the same trajectory as the corresponding electron in any other beam segment displaced in time by a wave period. This beam segment is divided into a large number of subsegments. We then solve the wave equation on the axioelectric field self-consistently with the relativistic Lorentz equations to obtain a fully nonlinear self-consistent system of equations for the system. We solve this system numerically and perform many simulations. I will show one simulation example. In this example, the normalized axioelectric field for propagation distance is shown. The signal frequency was 2 gigahertz and the injected electron beam was pre-modulated. The average current is 5 kiloamps with a 100% of the beam bunched over 1/4 of the wavelength. The electron beam energy was 1 mega electron volts with a relativistic mass ratio of 3. The input power is 9 kilowatts and the output power is 2.3 gigawatts with a conversion efficiency of 45% occurring at a distance of 1.4 meters. The efficiency as a function of propagation distance is depicted on the left, and the energy ratio of the electron beam subsegments as a function of phase at saturation is depicted on the right. We obtained an analytical estimate of the efficiency, and this agreed with the simulations. We found that a conversion efficiency is independent of frequency when the waveguide is untapered and the electron beam is unmodulated. To summarize, the interaction between the subluminal TM mode and beam mode is essential to the Cherenkov-Maser amplifier. This interaction allows for the amplification of input signals over a very wide frequency range. Operating frequencies are in the gigahertz regime. Output power levels greater than a gigawatt with an input power of 1 kilowatt and efficiencies greater than 50% have been simulated. Conversion efficiencies can be enhanced by pre-modulating the electron beam density or tapering the waveguide. Interaction lengths less than a few meters have been simulated. Excitation of the subluminal TM mode allows for straightforward coupling to an antenna, which is a significant practical advantage of this design. Professor Sprengel and I are submitting this research for publication in a referee journal. I'll gladly answer any questions in the poster section or chat.